when you try to evaluate a limit, the first thing you always want to try is direct substitution. So if we have the limit as x approaches 1 of x squared minus 4 over x minus 2, you plug in 1, and you get 1 squared minus 4 over 1 minus 2 is equal to 3. Limit exists. If you plug in 2, however, you get 4 minus 4 over 2 minus 2, which is 0 over 0. This is not 0, it's not undefined, it's indeterminate. So we don't really know what that is at this point, and so more study is needed, as we'll see when we start to solve limits analytically. Now, there are several properties of limits, such as the limit of a sum is the sum of the limits. You can put scalar multiples out front. You can move powers around. So here's a couple examples. If you were given that the limit as x approaches c of f of x is equal to 9, and we don't know what f of x is, we know where c is, that's not the point. What is the limit of this function as you approach c is 9, then we can solve an equation of this type by simply rewriting it. We can take the 3 halves and we can put it basically outside of these higher limits, so this becomes 9 to the 3 halves, this part. Over here we can take the 4 as a scalar multiple and put it out front, and so we have 4 times this limit, and we know that limit's equal to 9, so it becomes 9 to the 3 halves from here, divided by 4 times 9, and you get 27 over 36, which is 3/4. Another example, if we were given that as x approaches c of f of x is 16, limit as x approaches c of g of x is 8, and we have these two limits multiplied. Again, the power we can take outside the whole limit, so it's 16 to the 1/2. 3 is a scalar multiple, put it out front, so it's 3 times this limit, which is equal to 8. So 16 to the 1/2 times 3 times 8, 96. Over here, this can also be, basically these values can be substituted in. You could rewrite the whole thing and split it out in different ways, but basically you're just plugging in 16, you're plugging in 8, and you're evaluating it.